You all can hear me? You can't hear me. Is that better? Okay, perfect. And hopefully Zoom can hear me as well. Okay, good. Okay, so let me just sort of remind you, last time I said that we were going to try to prove sort of the same looking theorem for these three kinds of equations. And last time I sort of sketched this one. And in doing so, you only really need a couple tools. There's, basic energy estimates, this weighted Sobolev inequality, which I rewrote for you here. Also, can I ask, is this writing too small? Or is it okay? Sorry? Bigger? Okay, bigger. Okay. Okay, I'll try to write bigger from now on. Okay, so I wrote it for you here, just to sort of remind you what it looked like. This was Kleinerman's Sobolev inequality, and then you put these things together in the context of a bootstrap argument, and you could establish the result. I also realized I forgot to, mention a couple exercises, which I actually think are really good to do. And this is related to this weighted Sobolev inequality. So when you applied this inequality to the wave equation, what we got out of this was, pointwise decay of solutions of the wave equation, right? Something like that. And the point I want to make is just that there are sort of two features to these norms on the right-hand side here. The first is that you're taking some derivatives. In fact, you're taking two derivatives. The second thing is that these vector fields, the gamma vector fields, remember they had weights. They were things that looked like x dy minus y dx, or at least they could have weights because the translation vector fields are also here. If you want to show that solutions of the wave equation decay, you need both of those features. So having really rough initial data, in other words, initial data for which this norm is very large, because you take two derivatives, or maybe you don't even have two derivatives. That's an obstruction to proving decay. And having data which are not localized in an appropriate sense is also an obstruction. So just, these exercises, they're not very precise, but just think about solutions of the wave equation and try to figure out why both of these issues are necessary. So for example, you can construct examples of very localized but rough initial data for the wave equation, which doesn't really decay. And you can construct examples of very smooth but very delocalized solutions of the wave equation, which don't decay. Okay. Yeah. Yeah, this is just in 3 dimensions.
Otherwise, the same thing holds, like also less equal.
Right. So what if you sort of track the proof from last time in n dimensions? What you'll so maybe I'll just write this here in n plus 1. What you'll need is alpha less than or equal to the ceiling of n over 2. This is just because you apply the regular L2 L infinity Sobolev embedding theorem. And this exponent stays the same, but this exponent here becomes v, writing bigger, v to the negative n minus 1 over 2. Okay. Maybe. Okay, so this is great. Well, so first, are there any questions about, sort of this quick review? Okay, so this is great. You sort of have a way of showing, global stability of the trivial solution of this equation, which is a pretty good start. But we're really interested in studying equations that come up from some kind of physical system. So maybe the Einstein equations, right? That's one, or compressible oil equations under potential flow, things like that. And unfortunately, what you see is that there's one sort of structural difference between, well, there are a lot, but just to start out, one important structural difference is that the nonlinearities can tend to be quadratic instead of so so let's consider instead just some quadratic nonlinearity in first derivatives. I hope it was sort of clear last time that I chose partial t just sort of at random. It didn't really matter that it was specifically a partial t derivative. I'm doing that again here. This is just an example of some quadratic nonlinearity. And you might remember that last time, the key step in sort of showing that everything worked was when you tried to measure how much energy the nonlinearity pumps into the system, you would use this energy estimate, which looked something like this. So I was, we were just sort of applying this energy estimate and seeing what happened. And unfortunately, what you see is that sort of in the cubic case, when you looked at this norm, you exactly ended up having to integrate something that looked like this. And the reason for this was because, again, if you unravel the Holder inequality, and it's sort of an exercise to just work this out in detail, you could put two factors of this in L infinity. And in 3 dimensions, this is Kleinerman-Sobolev inequality. This 1 over v is basically like a 1 over t. And so at the end of the day, you end up having to integrate 1 over t squared from 0 to infinity. And the point is this converges. If you go through this exact same argument, but instead of using box phi equals dt phi cubed, you use box phi equals dt phi squared, you'll end up having to integrate. So maybe I'll write this is for let me make a small change here. I'm going to put a negative sign there. Okay, so for this nonlinearity, what you end up having to integrate is instead just 1 over t. So this means that your proof fails because at large times this integral diverges logarithmically. So at this stage, there are a couple possibilities. One possibility is that you've missed something, as in maybe this proof doesn't work, but maybe the result is still true, and you have to take advantage of something else. It turns out, though, that's not the case. So there's sort of a paper by Fritz John. I think this is maybe 81, something like that, around 1980, that says if you have any non-zero smooth compactly supported initial data for this equation, the solution blows up in finite time. So any non-zero smooth compactly supported initial data leads to a singularity. Okay, yeah. So So it's just, if you look at the proof, it relies on the sign of the fundamental solution. And I specifically, I think this is the correct sign to show that it will blow up to the future. This is just my recollection. Maybe it works. I should just say I don't remember, but I know that this is the equation studied. The sign, yeah. Anyway, maybe it's true for the other, but so certainly, by replacing t with negative t, the other sign will blow up to the past. But yeah, anyway, this will blow up to the future. Okay. Okay. So now you're in some trouble because if you have a general quadratic nonlinearity and you're trying to show a stability result, so either the stability result isn't true, or somehow the quadratic nonlinearity has some kind of important structural difference with this one. And you have to take advantage of that, because otherwise, the result isn't true. So let me just write down a lemma. This is a lemma that you'd have to go through, right? At least it provides a clean way to prove this inequality. So sort of this is one of the steps that I said, one of the two steps that I said you'd have to take last time to convert the proof of just the anisotropic rescaled Sobolev inequality into the proof of this statement. I'm going to state it. And then it's also going to hint about what kind of structural property the right-hand side here could have to make things better. Okay. So here's the lemma. So I'm, especially we saw Yakov's lecture yesterday. So I'm going to let L be the following vector field, and I'm going to let L bar be the following vector field. And I'm going to let nabla slash be the projected gradient. Onto the spheres. So that is to say, these are the spheres which are intersections of level sets of T and R. All right. So I'm now going to introduce sort of schematic notation. I'm going to use this partial derivative with an overline to denote good derivatives. And a good derivative will just be something for which this is true. D bar F is less than or equal to LF plus nabla slash F. So basically, good derivatives are either an L derivative of F or this, some sort of derivative tangential to the spheres, or some sort of combination thereof. If you think about what this is saying, this is just saying that good derivatives are simply derivatives tangential to level sets of U. So D bar So one question you might ask is why is it natural to consider any of this? So before I state the upshot, let me take a quick break in the middle of the statement of the lemma and give you another exercise, which is just sort of a modification of one from last time. So so recall spherical symmetry. which the equation was dv du of r phi is equal to 0. All right. By the way, dv and du are collinear. You can check to L and L bar. So last time we talked about how if this is the TR plane and you have initially smooth data supported near r equals 0, the solution would be supported in sort of a strip that looks like this. It would be 0 here, 0 here. And what you could say is that phi is like 1 over r here. And moreover, you take any number of derivatives, sort of random derivatives you'd like. And you should also expect this to be like 1 over r. There is one special choice of derivative here you could take in a specific direction in which this is only an upper bound, but not a lower bound. So the new exercise is show that dv phi is actually like 1 over r squared. In this strip. So this sort of tells you that for some reason, you know, although if you take a bunch of generic derivatives, nothing changes here. The behavior stays the same. If you pick it very special, in sort of a very special way, you'll do better, right? So we're no longer in spherical symmetry, but we're sort of perturbative off of spherical symmetry because, you know, rotation vector fields, we should think applied to the function aren't so big. I sort of talked about that last time. So I can hope that the similar structure holds, and hoping that this sort of tells me that L should be good. And again, you're perturbative off of spherical symmetry, so this should be good as well. That's why I'm calling them good derivatives. Okay. Now, with that little piece of motivation, let me sort of state the lemma I want to state. And this sort of tells you how you can use the vector fields that I introduced last time. These vector fields which satisfy nice properties with respect to box. They're generators of certain conformal isometry of Minkowski space. You can use them to sort of see that these are good derivatives. So here's the statement. If you take a good derivative of the of any function, the following is true. Generic derivatives, meaning ones that aren't tangential to the cone. In particular, they can pierce the level sets of U. They're worse. You can only do the following. So it's an exercise to show both of these statements. It's just sort of algebra. But all you're doing is, you know, you have these weighted derivatives, which should be well behaved. So in order to leverage that, it's natural to try to write these sort of unit derivatives in terms of those. That's all that this is saying. You can sort of write unit derivatives in terms of the weighted vector fields and gain that weight out in front. But there's a caveat, which is that for good derivatives, you can gain a factor of b, which is, I'll remind you, is t plus r. So this is sort of very small everywhere. Whereas for generic derivatives, you just gain a factor of u. U is t minus r. So along the cone, along the set where t is equal to r, this factor doesn't really help you. Okay? Are there questions about this? Yeah? Sorry? So if you start to reduce the number of vector fields that you have, these algebraic relations stop being true. But there are then other games you can play. for example, writing certain elliptic equations. So at least what I have in mind right now is, yeah, well, all right. There are other games you can play. Like, for example, all right. So, for example, one game you could play is, suppose you remove some vector fields, but to the right-hand side, you add box with some weight. Here, this is just about vector fields. You're nowhere using the fact that at the end of the day, these things are going to solve the wave equation. So, you don't just hope that these vector fields applied to the thing are small. You also hope that box applied to the thing is small. So you can regain some of these things by pulling tricks like adding things like box times a weight, maybe t times box of the thing, all right? But yeah, if you remove them, then this can stop to be true. Any other questions? Okay. All right. So this sort of hints to you at a structure that could help you on the nonlinearity. Because I can write, for example, partial t in terms of L and L bar. So what is this? This is L plus L bar over 2, right? So if you just sort of expand this out, you can see that partial t phi squared has an L bar phi squared piece. Right? So this motivates the condition that your nonlinearity should just never have this piece. If you have quadratic terms, you should never have something that looks like L bar phi squared. Because the bet you're making is it's this worse decay behavior, which is killing you. So this sort of the, historically the, well, the null condition is just sort of the natural geometric condition that that guarantees that this is true. So let me just write this definition out. So a constant coefficient bilinear form satisfies the null condition if Q of C equals 0 for any null operator. All right. So this is the definition, and this is sort of the key lemma, whose proof I'll leave as an exercise. So if Q satisfies the null condition, then 1 Q of d phi deep C. Maybe I'll write it Q of df dh. So you plug in two functions, or the differentials of two functions into the arguments of Q, and you can say that this is bounded by d bar f dh plus H. And the second fact is that null forms. So in other words, these bilinear forms which satisfy the null condition, we call them null forms, are stable under commutation. By any of the vector fields described before. This is important because in sort of the scheme, the scheme we described before, in order to take advantage of these kinds of things, you had to commute the equations with these gammas, right? And I want it to be the case that this nice structure, this kind of nice structure, which is what I hope will save a global result, survives after you commute. And this basically says it will. All right. Are there questions about this? Yeah. 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 If you put r to the negative epsilon, even just the sort of that original group will close. Well, so, so this step would be a little bit more, you'd have to break it up into a region away from the cone where you decay like t to the 3 halves, and then you're okay. And then along the cone, t and r are comparable. So instead of having this 1 over t, you'd have 1 over t times t to the epsilon. So this would, this would be like this in that region, just sort of using the fact that t and r are comparable. And so then the, yeah, you can see this because even like Fritz John's proof, okay, I should preface this by saying I don't remember this so well, but I'm pretty sure that like if you have like, so let's say your data are supported in this ball, and you just sort of go right up to the edge of the support. I think that his proof works looking at the fundamental solution and just looking at sort of the influence of, just this little piece along the light count. So in that region, U is comparable to 1 anyway. There are other situations where it is like not the behavior along the cone which kills you, but the behavior in the interior of the cone. For those, adding powers of U would, I think, save you. But that's not the case for this. So, for example, Ishti has an example of this. You take a system that satisfies the weak null condition. Sorry, maybe I should just tell you this later. Yeah, there are examples. Okay. Anyway, sorry. Any other questions? Yeah. Yeah, right. So you're sort of making the point that you can allow for L squared to appear and it should be okay. And that's true. So the theorem works for things that satisfy the so-called future null condition, which is that L phi, you allow for things like L phi squared, but those equations can blow up in the past because the role of L and L bar switches between t greater than 0 and t less than 0. So that's another exercise that you can sort of check for yourself. Any other questions? Okay. All right, so this is sort of the, I'm going to erase this because I need this space. So this is the next tool that we've introduced, is this null condition, this null structure. So I'll just call this nonlinear structure because that's the takeaway. As in, this is, you know, one of the most striking examples of nonlinear structure saving you, but there are others also. So you should be on the lookout for nonlinear structure. This particular nonlinear structure is the null condition. It's also called null structures. So this is the fourth tool. We're going to use nonlinear structure because we have to. All right. Okay. So so this is great. Somehow we want to take advantage of this fact. So it's very natural to try to use this lemma. So let me write down a consequence of this lemma and this estimate here. And I'll sketch the proof for you. So here's a proposition, and I'll call this improved decay. So so here's what we have. So I want a version which is about specifically good derivatives. So let me actually let me write it. Okay, yeah, I'll write it like this. And then this is okay. So here's the proof of this. The first is apply Kleinerman-Sobolev inequality to the function df. This tells us that df tr omega. By the way, I should say so this is true more generally. I'm giving a proof which sort of works specifically in the case. So maybe I'll just add this as an assumption. For f supported, where t is greater than or equal to r minus 10, let's say. So just to draw a picture for you, in the TR plane, I'm just saying that f is supported up here. And this is certainly the picture for solutions of the wave equation, which arise from compactor-supported initial data in, say, the ball of radius 1, right? Okay. So the first thing is you apply Kleinerman's Sobolev inequality to partial f. And this ends up telling you that this quantity behaves like v to the minus 1 times u to the minus 1/2 times other stuff. These sort of norms, which you'll have to keep track of. This is the first step. Then use fundamental theorem of calculus to say that f is less than or equal to the integral. So f of tr omega is less than or equal to the integral from r to infinity of drf of t r prime omega dr prime, right? Because you're assuming it's compactly supported, this sort of boundary term vanishes. And I should, yeah. So this is just fundamental theorem of calculus. My claim is this implies, if you just sort of plug in, you know, the inequalities you have here, this implies that f is less than or equal to v to the minus 1/2. All right. So I'll just finish it off over here. Now, do the same for gamma f instead, where gamma is any of the vector fields, and apply the lemma. By the lemma, I mean this lemma here. Unraveling everything, this tells you that gamma f is bounded by v to the minus 1/2. I'm just saying apply this argument that I just sketched for gamma f. And then by the lemma, this tells me that v bar f is bounded by one additional power of v. So this is v to the minus 3/2. So this is sort of just a sketch of the argument. But, you know, you can make this precise yourself and actually keep track of the norms you have here. I think this is correct, what you'll end up getting. Any questions? Okay, so this is great. We've shown that you know, indeed good derivatives are better, and we've done it in a way that just sort of relies on these vector fields. If you track all of that, which means that the hope we have is we can just sort of interface this very naturally with the proof that we used for y. Right? That's the strategy we have. Now, does anyone foresee an issue with this? There is an issue with this. So let me show you the issue. By the way, I won't prove this, but I should say you can classify all constant coefficient null forms, like explicitly. Just, you know, you can look it up in, I'll give you references the last day that cover everything I've said in more detail. All right, so here's the issue with this. If I commute the equation a bunch of times, what I sort of hope to be able to say is that this is bounded by something that looks like this. I mean, there are going to be all kinds of terms. Let me just write a couple of them down. You know, this comes from applying the Leibniz rule, essentially. Well, even let me just write one down, the problematic one. one. I'll write one more down. So you have a bunch of terms like this. You can sort of think that this term comes from when all the derivatives fall on the good derivative. And this comes from when all the derivatives fall on the bad derivative. Now, if you're working through this, suppose that alpha corresponds to your top order. Like this is the maximum number of derivatives you're allowed to take. You're not allowed to take any more. All I've shown is that good derivatives are better in a pointwise sense, but my proof of that relied on taking even more derivatives. So if I wanted to say that this is better, I'd want to use this proposition here, essentially, plugging that in right here. And you can see that that sort of schematically loses 3 more derivatives. And I can't do that. I'm not allowed to do that. With this term, it's okay. Because I can think that this is, the order, the number of derivatives I'm taking is a large number. Last time I said 100. So, this is on the order of 100 here. All I need is to be able to lose 3 on this. And I can definitely do that, right? But this is the issue. So the bottom line is you have to show not just that you're better in a pointwise sense, but also that you're better in an L2 sense. So this is the next tool that we need, and this will end up being the last tool that we need for doing this problem. So I'll call this energy estimates. So this is sort of part 2. And what this means is, so using other fluxes. That's kind of ambiguous. Using other hypersurfaces. And I'll sort of show you what that means. Also, tomorrow, I'll actually show you yet another way of showing improvement in L2 using these sort of part of the P estimates, but that's for tomorrow. So how can we show that this is better in L2? That's what we need. We have to show that somehow this is better in L2. So if you think back to just the standard energy estimate, what you did is you took box phi, you multiplied by some vector field v applied to phi. This vector field was actually partial t, and you integrated by parts in some region. In fact, you integrated by parts in sort of a space-time slab between t equals s and t equals 0. So the first thing I want to point out is very schematically, that you have even more freedom, but very schematically, just if you're following this recipe, you should think that you have like 2 choices you can make. You get to choose V. And the other thing is you get to choose the regions in which you, sort of the region in which you integrate by parts. It's very natural to choose t equals 0 as sort of a bottom bound for the region you're going to integrate by parts, because that's where data is naturally prescribed, at least in this setting. This is what you do in well-posedness, but if you think about it, you don't really have to do that. You can choose other sort of upper bounding hypersurfaces. So next time, I'll talk about sort of nice freedom with the V, how changing V can help you. This time, I'm just going to talk about how changing, in particular, this can help you. All right? So what we're going to use is a characteristic energy estimate, meaning I'm going to integrate by parts between t equals 0 and a level set of u. Oh, sorry. Let me. So this is u equals constant. This is still t equals 0. And I'm going to do exactly the same thing as I did for the wave equation before. I'm even going to use the same v, just dt phi. I'm going to look at box phi, multiply by dt phi, and integrate by parts. So exactly the same thing as before, except I'm doing it in a different region. So here's the claim I have. This is what the estimate tells you. Roughly speaking, up to constants. I won't keep track of constants. So what it tells you is that let me even be ambiguous about that. All right. So this is what the energy estimate tells you. Amazingly, you still get a positive definite or negative definite flux. It has a sign on here. But it looks different. In particular, it only contains good derivatives. So this is nice because this is an L2 estimate of exactly the quantity that you're sort of banking on being better, right? You still have this initial beta term, and you still have this error integral over the region omega, where omega is just this, everything that lies above t equals 0 and below the cone. Right? Are there questions about this? Oh, yeah, thanks. Sorry about that. By this, I mean the sum of all good derivatives squared. So this is like L phi squared plus the length of the angular gradient of phi squared. All right. So, any questions about this? Okay. So why does this help you? Trying to think of how much I should say. All right, I'll let me say a little bit. Okay, so excuse me. So this estimate certainly implies the following, which so this implies sort of the following: the space-time integral of bracket u to the -1 minus delta times good derivatives of phi squared So why is this true? This is just because this is a function of u, the right-hand side is not. All I've done is multiply by the L1 function of u to the -1 minus delta, and integrate it. So, this just follows immediately from this upon integration. So this tells me that I can get, so first, like, look at this integral. This integral is very, very good when u is small, when u is like 1, meaning very, very close to the cone, because that's sort of telling me that this thing behaves in an extremely good way. It really does behave better than generic derivatives. Here's a simple exercise. You can do this in spherical symmetry. Show that the integral over the region where u is less than or equal to 1 generic first derivatives of phi, meaning including the bad derivative, show that this diverges. For non-zero smooth compactly supported initial data in the unit ball. But this thing here tells you that this quantity, if you just put in good derivatives, is finite. So this truly is a measure of this being better in L2 than this. Sorry, that good derivatives being better in L2 than bad derivatives. All right. The only thing that's kind of unfortunate is you have to pay with this weight here. So I'm now just going to say in words, so that I can say a couple other things, how you actually deal with this term. The way you deal with this term is you now use the fact, which you actually had not used before in the old proof, that Kleinerman's Sobolev inequality, this inequality here, it doesn't just gain you a factor of v, it actually gains you a bit of u as well. So you can use this factor of u, which you can think is tied to this thing here, after you apply Kleinerman's Sobolev inequality, borrow that weight onto here, use this estimate, and everything will be okay. I'll leave you to figure out how that works. But hopefully it just seems plausible. Like, I have some free powers of u here. So I'll just use that. I'll just leverage that to get what I need. All right. Questions? I know I don't have time to do it out as much as I'd like to, but just broad strokes. Any questions? Okay, so the last thing I wanted to say is when you start to think this way, that when you start to think this way, that you have freedom in the choice of V and freedom in the choice of surfaces, it can start to get very messy. Even doing this computation for just what I said here isn't so simple. I mean, doing it in coordinates, it's not great. So luckily, there's a tool which can make parts of this computation very systematic, which is the so-called energy momentum tensor. From a purely mechanical point of view, this just takes this process of taking box phi, multiplying by something, and integrating by parts, and makes it systematic. It actually comes from a sort of more like a deeper place, but you can just take it to be that. It's a systematic way of doing this. And the energy momentum tensor is following. So I'll call it Q of phi. So this is the energy momentum tensor of the scalar field phi. And this is just equal to d phi tensor d phi minus 1/2 g of d phi d phi times the metric g. Of course, now this is all with respect to the Minkowski metric, so this metric g should just be the flat metric. But one nice thing is that this geometric object works on a general manifold. So this energy momentum tensor makes sense. On a general Lorentzian manifold equipped with a Lorentzian metric G. Here's the key property. Well, maybe I'll just list some of the key properties. Well, one thing which is sort of immediate to see is that this thing is symmetric. But the other sort of key property is that this thing is divergence free. It's divergence free, specifically assuming that phi is a solution of the homogeneous wave equation. More generally, the divergence of this, and this is an exercise, you can show it's equal to box G phi times the 1/4 d phi. All right. So this sort of tells you, this really hints at how this is the same thing as doing this. If you want to do energy estimates in this geometric way, you contract the energy momentum tensor with a vector field V, and you take the divergence sorry. You contract the energy momentum tensor with your vector field V, and you use the divergence theorem, which is just sort of systematically integrating by parts, and you'll naturally end up getting, when the divergence hits the energy momentum tensor, something that looks like this contracted with V. And that exactly sort of looks like what you had up there. All right. So for the course, this is sort of for the lectures, I don't have time to really go through and prove all of these and other important properties of the energy momentum tensor, but it's good to be aware. Then you can look it up in a bunch of sources. And yeah, I'll stop there.